Okay, so let's get started with the last session of the day. This will be given by, the talk will be given by Ankur Das from IISc Tirupati, who's going to be telling us about short noise in solving bulk and boundary puzzle.
Thank you very much. And thank you for giving me this opportunity to talk to this excellent conference. It's a lot of interesting talks. So I'm going to tell you a slightly different story. So people want to get rid of noise, and I'm going to tell you why noise is not that bad. It actually can help you to know about a lot of things and why this is important. So I wrote about something about bulk and boundary, and I'll explain what this puzzle is, why we care about it. Okay? So the works has been online if you want to take a deeper look, how they're connected to this story, but I'm going to give you the summary of it, so how to think about it. Okay? Stop me and ask any question at any point of time that you need. Okay? And doesn't have to just wait for the last. If you have immediate question, please stop. Okay, so let me start why we care about it. So for a long time, we are trying to do braiding statistics in quantum computing. There are many platforms people are trying. And one of the things that people want to do for a long time to use topological insulators. Okay, you may have heard of it. I know a lot of you have heard of it. But why? What is different as topological insulator? Just for a quick reminder, it's different for what is called a vanilla insulator, and it's different because both of them have gapped bulk. However, vanilla insulator also have gapped edge. It's gapped all through. However, topological insulator is not. It is actually gapless at the boundary. Okay? And the idea is to use these edge states for braiding. Okay? And it happens to be true that the oldest known and the simplest example of a topological insulator is actually quantum Hall. Okay? Now, this picture of this edge mode and the bulk is actually too textbook. Okay? In real life, it's not that happy, and this is where I'm going to come, that what this bulk and this boundary both holds puzzles, and we don't know the answers always. Okay? I'm going to come to that. So, as I said, there are many platforms. There's anomalous quantum Hall, twisted bilayer graphene with a fractional churn insulators, superconductor TVG junctions, non-abelian states in quantum Hall. I'm going to tell you a little bit about it. Quantum Hall in graphene, not only just 2D electron gas, and superconducting van der Waals system. These are all kinds of devices people want to use to do quantum computing. And you can see quantum Hall, at least I've shown a few times, churn insulators and quantum Hall show up in a few places. So if you want to use them, it's better to know what you are using. Not only better to know, we have to know. And it's better to nail down what is the true nature of the phase that we're going to use for it. So this is just to tell you why it is important. Let's go to the meat of it. So quick reminder, what a Hall effect is, classical Hall effect is. I think you have heard it probably like 5 times already, but let me tell you once more. So you have a 2D system where electrons are moving in the 2D pair. And as you have a potential difference, there is a current. And put a magnetic field which is perpendicular to it, and you find there is a potential perpendicular to the electric field. Okay? You can explain this using Lorentz force, and then you know this Hall coefficient actually increases linearly with B. Okay? And you can also write down the Hamiltonian for it. This picture gets muddied when you really make the sample clean and when you go to the low temperature. Okay? So what happens, this straight line actually breaks into these plateaus. Okay? All these plateaus. And you will see that I have also plotted the rho xx. So this is a tensor. I'm also plotting the rho xx and rho xy. And this rho xx has this jumpy behavior. Okay? And this goes to 0 in specific spots. And you can explain this by quantizing this Hamiltonian into what are called the Landau level energies. Okay? And these Landau levels are given by this n number. And one of the simplest example where you fill up all the Landau levels, that will give you a quantum Hall effect, and that is n equals to 1, which basically means that for n equals to 0, you filled up all the states that are available. Okay? How many states there are available? As many flux quanta that your system can hold. That many. Okay? And there could be, as you can see, other things which are also there. Okay? So you see that this factor, h over e square, defines the quanta. And you can see that it also comes in fractions. Okay? I'm going to come to it. Now you see the rho xx, as I said, is 0, which means this bulk is gapped. Okay? And rho xy is non-zero, which actually signifies that the edge is conducting. Okay. So there are many, many fractions, 2/3 being one of them, as to 5th. One picture that kind of helps us understand this is what is called a composite fermion picture. Okay? What this picture tells you that there is a bound state of a flux, pair of flux, and the electron, and this object also behaves like a fermion. Okay? You can bound 2, you can bound 4, you can bound 6, you can bound different set of even number of fluxes, and these objects will behave like fermions. And these fermions in the leftover magnetic field produces an integer quantum Hall effect, sometimes called the lambda level. Okay? And you can see there's an example from this book by Janendra Jain, where you can see there are 10 fluxes and there are 4 particles. So the filling fraction is 2/5. Okay? And as I captured or made a bound state out of it, now there are 2 flux and 4 particles. This is integer Landau level 2. Okay? So you get a Landau level 2. And this is the general formula for the effective magnetic field and the filling fractions. Okay? From the structure, you see the denominator is generally an odd number. But there are special cases, and I'm going to come to that when it goes beyond, how to think about this. Okay, so what is this 5/2? Where does it show up? I didn't show it yet. So you can see this 2, 1/2, and 3/2. These are in locations. Okay, these locations are where it's not the R-axis does not go to 0. Okay, but however, this is the zoomed in region here, and you can see that around 5/2 this starts going down to 0. And in this is a very old result, but nowadays it goes all the way to 0 for almost half a Tesla. Okay, so it really goes down to 0 and it becomes a flat plateau. Okay, so there is a plateau there. It's a non-trivial one, and the Jain fermions does not explain it. Okay, so we want to focus on that because this is one of the things. But let me tell you first that when I said that we have to go beyond textbook, what do we really mean? Okay? So these are examples of very simple quantum Hall states. So n equals to 1/3 is like n equals to 1. Okay, it's just fraction, it's 1/3 of the filling, and there's a 1 mode that goes by. This we just checked out, right? This is like integer lambda level 2. So there has to be 2 modes. Okay? And then, this is something called a hole-like state. So you can think as a 1 minus 1/3, right? 1 minus 1/3 is basically 2/3, where 1 mode, it's 1 which is going this way, the 1/3 goes the other way. It's counter-propagating modes. Okay? However, this picture is very simplified, and it was known to us from very early time. So even if you take a very simple integer quantum Hall, you know, the quantum Hall, you have to define some potential well, right? Where you are trapping the electrons. It turns out this trapping part is not that sharp in general, right? There are no infinite potential in real life, so they are actually quite soft. And you can show that if the trapping potential is soft, then there are new counterpropagating pair of modes can show up, okay? And not only is n equals to 1, it was shown by Wang Mer and Geffen that in n equals to 2/3 also it can happen. Rather, it actually happens all over the place. It's actually very hard to get rid of it. Until very recently, that was described by Mike Manfra. It's actually really hard to get rid of them. So that's one problem. So single mode, the dream case is not always true. And in graphene, we don't even fully know what to do with this. It's even more unclear. This is all I'm talking about 2D electron gas. Okay? There's also something called a disorder interaction unequilibrated regime. So let me explain what I mean by that. So let's take these examples. So there's a 1 and 1/3 that are going counter-propagating. So if there are disorder in the system, this disorder will allow charges to tunnel from one to another. Okay? And because they are charged, they're also interacting. And you can show that if the interaction in the disorder strength is large enough, they can go to a new RG fixed point. And this fixed point consists of one charge mode and one neutral. One way to think about this is like a dipole mode that goes in the counter-propagating direction. And it was first discovered by Ken Fisher and Polchinski, and by the name it's called a KFP fixed point. Okay? And this can happen. So even though the picture is this simple, you see this picture is much more complicated and gives you something that you don't expect. Okay? It can go even more complicated. So it was first discussed by this set of people, Yuval Geffen, Sasha Milne, Bernd Rosnew. What they discovered is that there is something like a hydrodynamic regime also, where this edge modes actually loses almost all of its quantum information, like all the quantum nature of it. It's a completely decoherent system. However, it only depends on local objects, local thermodynamic quantities. I'll explain what I mean by that. And all the quantum quantities, or the quantum Hall effect and quantum thermal Hall effect, they remain identically same. Okay? So this is another regime. And all of these can happen depending on what's in your system. And none of this breaks topology. So it turns out topology has a very weak protection on very specific quantities. Specifically, it can conserve the quantum Hall and the thermal Hall. These are the only two things that it can conserve, okay, that can preserve. Rest is anybody's game. Okay, so 5/2 is even difficult from this. Okay, I'm gonna come to that. So what is 5/2? So in the 5/2, it turns out the bulk state is even like complicated. So there are many options for the bulk states. So what are they? So let's try to understand. So 5/2, you can think of as 2 plus 1/2. So this is the 2 part. Okay, so these represent integer modes. And then there are 2 sets of predicted states for the bulk that has been proposed over time. These states, you see this dashed line, which are called Majorana modes. These Majorana modes are not present. Here, the Majorana modes are present. Okay? One can describe this problem that these wave function, the excitations in the bulk, have abelian behavior, and here they are non-abelian behavior. What it means that if you take 2 excitations, take them one around the other, okay, these excitations don't pick up a phase, it goes to a completely different state, an orthogonal, completely different state. This is one of the reasons we want to use this for quantum computing. Okay? And you can see the ones on the top have no counter-propagating modes. The ones in the bottom have counter-propagating modes. These are whole light states. These are called particle light states. And this specific one, the green line one, this specific one was proposed by D.T. Sun in 2015, where he said that it's possible the state does not break particle-hole symmetry at all. And there's something called a particle-hole Pfaffian state. Okay. So this particle-hole Pfaffian state was not discovered until 2015. However, it turns out it's very hard to simulate them, so there are very little numerical evidence for it. Okay. So the idea how to detect them. So I messed up something. So this kappa is the thermal conductivity, okay, in the thermal quanta. And Majoranas you can think of as like a half fermion, which means it gives the half conductivity. So you see that if these red ones, any of the red ones are the candidate states, thermal conductivity would be a natural object to measure. Okay? And that's what people did. In 2018, this is Moti Heidblum's lab, and Mitali Banerjee was the designer of this device. And what they want to do, they want to just check the 2 terminal conductors. I'll show you right now what are the predicted values. So the predicted values for the kappa for these are all integers, as you expect. You know, these are non-abelian states, abelian states. These are non-abelian, and you can see 4.5, 3.5, it goes from high to low, continuous, okay? So the numerically most predicted states were Pfaffian and anti-Pfaffian, okay? So this measurement is precisely solve this bulk puzzle. So you can see how many candidate states there are. And this is a puzzle that they wanted to solve. And they thought they will measure it. One of these two has to be the solution. Neither one was. Okay? The measurement gave 2.5. And there was absolutely no idea why this is the state. Okay? There was absolutely no theoretical understanding still today why this is the answer. And people have tried to answer it. There are two groups independently discussed that what can happen, that disorder can pin Pfaffian somewhere, anti-Pfaffian somewhere, and you make interface between them and you fill up the whole space. Okay? And they describe what will happen and something like a thermal metal that will show up. Thermal metal means that in the bulk, there is no charge conductivity, but there is heat conductivity. Okay? So through bulk, heat can go, charge cannot. Very bizarre objects, right? Because you cannot do the Lorentz number that just blows up. Okay? But Steve Simon showed that for this to happen, the disorder strength has to be so large that quantum Hall itself will die. Okay? So we still don't know what's the case. There is a second proposal that came in. And for that, I have to explain what equilibration is. Okay? So now I'm coming to that. So this is, previously saw this picture. These are tunneling bridges, randomly located. We separated them, but in reality, they are randomly located. And I'm going to focus on two of them, and I'm going to zoom in there. Okay? So I want to define some thermodynamic quantities for these edges. Okay? I'm going to define that. I'm going to claim that if I take a virtual reservoir where its voltage and temperature I can tune, okay? And I can have a very weak tunneling bridge which allows current to flow from this virtual reservoir to the edge, okay? I'm going to change my V and T, okay? Similarly here, there are two independent ones. I'm going to change my V and T as long as the current on this weak tunneling bridge does not go to zero. And when it goes to zero, then I'm going to say that this reservoir is in equilibration of this local location. So that is the definition of a local chemical potential and local temperature. Right? That's the definition I'm going to use. And you can solve this. So you can see there are tunneling currents coming in, currents has to be conserved, and you can actually figure out what the solution is. So these solid lines are these two. On the other end, there are this, because there's a quantum Hall, right? There is another edge here. There's these dotted lines. And you can see that bizarrely, this potential remains almost the same and then suddenly drops. Okay? This length scale comes from some internal parameters that is impossible to gauge from a theoretical perspective. But only around this length scale, the potential will drop. Everywhere else, the potential will remain same. So electron that is traveling from the source is coming, and then it jumps from the potential, it loses energy. That energy has to dissipate somewhere, right? The energy has to go out, and that will create a hotspot there. Okay? So you heat up the system. Okay, so, but what is important is these two modes, when they equilibrate, these length scale, so this large L, which is the distance between S to D, has to be much, much larger than this equilibration length, and only then it will happen. And that gave an opportunity for people that this might be what is going on. See, there is something called a partial equilibration regime where the Landau level mixing does not happen. Okay? Lower Landau level doesn't talk to the higher Landau level, higher Landau level doesn't talk to the lower Landau level. And if that is true, then anti-Pfaffian is still an option. Pfaffian is out of the game, no option anymore. But anti-Pfaffian, still an option. So the puzzle remains. So what's really going on? The problem is, because these internal length scales are very hard to measure or even control, Actually, you import filter control, but you can make many devices and hope it equilibrates properly. It's not easy. Okay, so, and then one thing they missed, so I haven't explained it here, but I only talked about only one equilibration length, because at that time it was believed that the charge and so the chemical potential and temperature both can equilibrate over same length scale. It turns out that is not actually the case. And these two papers actually showed that explicitly. This is from Anindya Das's lab, and this is from Moti Heiblum's lab. They independently measured that it is possible that the charge equilibrates, but the temperature does not. Okay, very bizarre. And it has been repeated by actually many other independent experiments you will find later in other papers in the supplementaries. But these two were the first two to actually see this. Okay, so we have to remember that. Okay, so what other signals there can be? Okay, I have done a lot of introduction of what the puzzle is. So let's try to give you the answer. So how to figure it out? And this is where the short noise comes in. Okay, so let's try to understand the hotspot I previously mentioned, how that can create noise. Okay, so see, there is something very funny in this one. So this is nu equals to 1 minus nu equals to 1/3 minus nu equals to 1/15. This is nu equals to 3/5. This is a very known, famous hole-like state. But see, the heat, if it fully equilibrates, completely equilibrates, then the charge will go this way, because it's 1 minus 1/3 minus 1/15 is greater than 1. But 1 minus 1 minus 1 is minus 1, so the heat will go this way. These are called anti-ballistic quantum Hall states. Okay, so this one goes, charge goes this way, heat goes that way. Very bizarre objects, but they do exist. So what is the process? How the noise gets created? So what happens, as I told you, you can think of that charge cannot go that way. So what can take energy? The next best thing, a dipole. Okay, so what the dipole does? The dipole starts moving. And at some point, the dipole can break apart. Okay, and when the dipole breaks apart, they starts moving in their corresponding direction. However, remember, because of charge equilibration length, it actually tunnels up. It cannot go much farther. And both of them end up at the drain. So you don't see any noise. Okay? What happens when they can go even farther? So they move, they go all the way close to the source, and then they break apart. The moment they break apart, now, if it is close enough to the source, less than the charge equilibration length, it can actually end up in the source itself. Okay? So now drain will randomly, sometimes will have a plus charge. Sometimes it will have a minus charge. Okay? And that will create a noise. So the noise is created very, very close to the source, which I will call a noise spot. Okay? It is. Okay, so this is our design. So what you do, you choose these three regions. You control, you have a back gate that will control the filling fractions nu, and you have a top gate that you can put on, change your potential, and make it a different filling. Okay, this is easy. This is which direction the charge is going, because I will choose always one of them nu and nu I to be 5/2. Okay, that's what I want to test. That's why it has to be one of them. But I will always assume full charge equilibration, and I will always assume that nu is greater than nu I. Okay, which means not all the current that goes from here can go that way. And because nu is greater than nu I, the average current will go this way. Okay, okay. If that happens, then I can measure the noise at D1 and D2. Okay, so let's see how noise can be created. Oops, there's a doubling. Yeah. So let's start with nu equals to nu2. Okay, so this is nu equals to 2, this is nu equals to 5/2. Okay, so now let's see. I told you about the hotspot when there is a source and a drain, where the hotspot will be. So there is a higher potential current like this is from higher potential is coming this way, lower potential coming this way. It could be 0, but in general there is just a V1 minus V2. Okay? So look at the arrows. So when it comes here, the current has to go this way or that way. There's no other option. So it does that. Similarly for here. And they meet at these two locations. This is where the potential drop will be, and these will be the hotspot. Very nice. But after that, so now let's look at one at a time. So let's look at the Pfaffian. So if you don't remember how Pfaffian looks like, don't worry. Here is how it looks like. All of them co-propagating. You have two integers. There's a bosonic and there is a Majorana. Okay. How does the nu equals to 2 looks? It's two of them going upstream. Right? Remember the chirality. So this red and blue actually will destroy each other. These double-lined ones. Okay? And you can see all the modes are going downstream, which will tell you that the heat is going exactly the direction the charge is going. Okay? Which means this hotspot cannot send any heat in that direction. Okay? All the heat has to go to D2, which means it will have no noise. Fine? I'm going to use this logic to the next one. So if you look at pH Pfaffian, if you don't remember, again, this is how it looks like. You put the integers, they destroy themselves, and now one goes downstream, one goes upstream. See, something funny can happen now, right? But this one is half thermal conductivity, this one is 1. So it still goes down. No hope yet, okay? Still goes down, same story, no noise. Anti-Pfaffian, what does happen now? Okay, let's go back. Now, I'm again going to put the integers, I'm going to destroy them. Let's look at what is left over. Something funny. This one is 1, this is 1.5. So, this time, heat goes up. So, dipole goes up, and it can break apart around here. But remember, if it breaks apart here, this has to go this way. When it breaks apart here, it has to go this way. So there will be noise created in these two locations. And this will only the only one that will have noise. Okay, direct. Okay, you don't need to know what is the values and everything, you will have noise, period. Okay, okay. What about 7/3? Now I'm going to not do the dance, I'll show you the answer. So this time, this is still parallel, no noise. pH Pfaffian now will have anti-parallel, will have noise, and anti-Pfaffian will have noise. Okay? So if I collect these three, you can see that now I have a direct measurement of zeros and non-zeros, directly telling you what is the state. But I told you, it is too simple. I assume thermal equilibration and charge equilibration both. What happens when it is partial? Here is the full table. I'm not going to go to full details of how to read this. I'm going to always assume full charge equilibration. And this is like partial means no Landau level mixing. And you can see, one case you can only detect anti-Pfaffian, all are 0. In other case, you will detect Pfaffian because it was 0 before and then changed. And in this case, only for it was 0 before, now it is non-zero. Okay? It's all in the paper. Please, if you want, go to the details, but you can actually tell all of them. Not only that, you can also tell from these changes. You can see it jumps by a factor of 2. This actually experiment can measure. And you can tell in which equilibration regime it also is in. Okay? So how to extend this? So this is the final result of this work. But I showed you some other work, so let me tell you how to extend this to other systems. Okay? Turns out, probably many of you have heard about quantum-point contact. What is it? It's a constriction. So this is the quantum Hall. You push the boundaries close to each other, okay? And they start tunneling to each other. Okay? This is actually how the 1/3 charge and 1/5 charge was first measured. But it can also happen sometime that there is a small quantum Hall liquid that's created at the tip of the QPC. Okay? If that happens, I can zoom in, I can redesign, And that problem maps to this problem, exactly same. Okay? Only this time you have to remember these regions have a different length than this region. It's not symmetric anymore. Okay? Okay? So short noise signature, the 5/2 I talked about, and these are Fano factors. They're basically current to noise ratios. But you can also use for 2/3. I told you, right? The 2/3 has options of being equilibrated and being in the KFP fixed point, given the Wang-Meyer-Gaffin fixed point. And you can also actually tell. You can measure the conductivity and you can tell what's going on. And this actually was seen very recently by Mike Mantra's group, where they saw half conductance even in a abelian case. Very bizarre. Okay? And there are other non-abelian states that we have worked out also recently. Okay? So what are the future prospects of this story? So one of the things that I said, understanding other quantum Hall states, some of them, of course, I did, but this paper has a lot of them. We haven't done all of them. But there is also this identification of 12/5. This is what we are working on recently, on understanding what a 12/5 state is. There are many, many candidate states there. Okay? And we want to understand if we can figure out the 12/5. Why do we care about 12/5? Because it turns out 12/5 can create universal quantum gates. Okay? It has been like sorted after for a long time. It can affect also graphene quantum Hall edge. And I don't want to go into full details, but there is an anisotropy part in graphene, which is a mess already for many, many reasons, even at zero filling. Okay? Graphene zero filling doesn't mean empty. It just means that you are at the middle of a particle hole symmetric point. But graphene fractional states are even more complicated. If you have been looking at arXiv recently, even a 1/4 state has been seen. Not just half, 1/4, which is a higher order non-abelian state. And there are many, many abelian states, not only 5/2. Bilayer graphene actually have all halves, from -7/2 to +7/2. All of them. Okay? It's absolutely not understood. Whole lot of MS. You can extend to other topological insulators, and you can also extend it to fractional Chern insulators, which has been seen in twisted bilayer graphene, for example. Okay? And we rarely understand fractional Chern insulator with respect to quantum Hall, because this has been being studied for 40 years now. Okay? So with this, I'm going to say thank you. And it looks like I finished early, and I haven't bored you long enough. So please, more questions. So this is IISc Tirupati, by the way.
Ankur. Yeah, Paramita. Is there a mic?
Yeah, hi, thanks, Ankur. So the question is there any role of the length of the junction? Like, does it matter whether you have a short or long junction for the interface case? Yes, this LQ.
Yeah, we actually have results. So it matters that the relative length scale of LQ to different equilibration lengths. And we don't know the LQs beforehand, but we can calculate for any possible LQ.
Okay,
so we can tell that.
At the last slide of your introduction,
yeah.
so whatever one of them going to the source, one of
yes.
them going back to the drain.
Yes.
So if you have a very long junction,
yes.
so we'll have less probability that they will reach the drain. Is it like that?
No, because it is ballistic.
Oh, that's why you have whatever length you have.
Yeah, so once you are on, so let's see. A little bit ahead, give me a second. Going fast. Yeah, this one. This is previously. Yeah, this one. No, not this one. No. This one, yes. So
I think you have a better picture if you go to the, I think last slide of your first part.
This one?
A letter? Yes.
This one?
Yeah, close.
So remember, this is 1, thermal conductivity 1, this is thermal conductivity 1, this is 1. So this is -2 and this is +1. So -2 wins.
Okay.
So heat will go this way. If it is not, if it's both -1, then it will only diffusively go that way. Okay? And it will depend how far you are.
I see. Thanks.
Yes.
Are there any other questions? If not, we thank Ankur for a very nice talk.